Goswami.
Sir.
Professor Goswami has completed his PhD from Princeton University and he is postdoctoral fellow from Harvard University. He has also worked in Brookhaven National Labs, New York. He is the recipient of several academic and research accolades including Wellcome Trust International Senior Research Fellowship, United Kingdom, the Swarna Jayanti Fellowship and Thatachaya Science Award, India. He is a fellow of Royal Society of Chemistry and several academic and professional societies and councils. Currently, as a professor in Department of Chemistry, IIT Kanpur, he is working on femtochemistry and experimental coherent control for spectroscopic enhancement. Some of his notable contributions are in thermal lens spectroscopy, coherent control, microscopy and optical trapping, quantum and nanocomputing, optical tweezers, bioimaging, etc. Please join me in welcoming Professor Debabrata Goswami. Today he will be delivering lecture on quantum information processing and computing with light.
Am I audible?
Yes, sir.
So I don't need to wear no, good. Let's see. So you have been. This workshop is on micro and nano electronics. So I thought I'll give you. This is the last lecture that you are having. So I'll give you something which is forward-looking. This is where the world is supposed to go, where we are trying to see if we can do the new kind of a computation based on quantum information processing, and much of this information processing is done with light because that's the easiest mode of transfer of information. That's the reason of this particular area, and as you do that, it also helps us if you can include the computation and information processing using quantum aspects, which gives you secure channel as well as robustness. I'm lucky to be at IIT in the sense that we have lots of students, and so our list of support from student group is a major advantage that we have. And as teachers, many of you would recognize that students have a huge impact on what we do. We have been supported well from the government as well as international areas in terms of funding that is necessary. Now, just a couple of very simple slides, which is to deal with the fact that we are talking about a computational paradigm which goes back to the very beginning of how computers were thought about, not as to what we are currently looking at, but to the basic notion of computing which started with the Turing machine. So in that sense, it's essentially the idea which recognizes the principle of computation. That's where you have to go back to if you really want to bring in a new paradigm in computing. So that's why this slide is presented to make you understand that we are not talking in terms of today's computers in that sense. Today's computers are a very well-developed piece of machine, but we are talking or looking at it from the principle where the whole idea of computing started, which is called the Church-Turing principle. So the reason for coming to this is a slide which is borrowed from Intel inventor Gordon Moore, who expressed his concern long time back on the fact that the size of the chip that is doing the computing will become so small that it will not be able to do classical based information processing anymore. And this was recognized by Paul Benioff in the National Labs, Argonne National Labs, who brought this problem to Feynman. And this is where the famous ideas started, and many people attribute this principle to the beginning of nanotechnology also. That very famous quote which is often taken from Feynman, there is still room at the bottom. All those are attributed to this very simple fact that it was recognized that the chip size will come to a point where this distance over which switching will happen would be in terms of distances which are attributed to electron motion. And that is one of the places where this has become a major thing. So what is it that's different from classical quantum? The basic difference lies in this overall idea that classical events that we talk about are nothing but zeros and ones, which come because of electrical circuits being high or low. These are just binary bits which are characterized in sense of being 0 and 1, and that's how it is represented, and we talk to them as bits. If you get into the quantum world, you can think of any two-level system to be a similar object for you. But the difficulty is that in the quantum world, whenever you measure, you do see the same impact of being one or the other, but until you measure, it's a Pandora's box. Until you see it, it can be anywhere. And that is the difference between a quantum bit and a classical bit. The classical bit is always defined in terms of the voltages being high or low, whereas in quantum states, it's not so. Unless you see it, it can be anywhere. It can be anywhere in the middle. And that's the principle of superposition, which is different. And that brings in the power, which we call as the power of computing. Now, in terms of looks, this is what you are asking the question, that when we originally looked at a principle, which is the Church-Turing principle of 1936, which became a machine later on during the World War times, these were machines of sizes of this entire, not this room, maybe 3 or 4 times this room size. And there are many movies which actually show pictures of those type of maniac machines which are of that size. And now, as we know, these have grown smaller to a point that this is good enough to, in fact, this particular mobile or even smaller ones are more powerful than the ENIAC machine, definitely, much more powerful. And so these have evolved to a much smaller point. But if you want to go and revisit, you would expect that you start from there. That's exactly what has happened. Today's quantum computers are not machines of this small size. They essentially represent that era where, like my lab, will be 4 times this size, trying to develop 1 or 2 chips, the 1 or 2 bits of the same kind. And that's how you have to scale and see how things happen. So it's like a reset of time. You go back to the dinosaur era to start back your time. So I have already talked to you enough about quantum, but the general representation in this form is given in this particular picture where you are trying to visualize. So one of the problems of quantum, which everybody has, including Feynman, who kept on saying that he was collecting pebbles on the seashore, even towards his end days, in terms of understanding quantum mechanics, is that its physical picturization is very, very difficult. So when I teach a course on this quantum computing, so and most of my students are from non-quantum mechanics background. So the first thing I tell them is to believe in what they know, which is linear algebra, and let go with it, and don't ask any questions of its physical significance, because that creates a problem. You believe in math, you believe in linear algebra, you do parallel linear algebra, means you do sets of linear equations, solve them, they're all perfectly fine. That's exactly what you keep on doing when you're looking at quantum mechanics. Don't ask, why did I get a solution which I cannot physically understand? That's the problem here. If you ask that question, then a lot of difficulties coming from it. If you do the math right and you get the answers, then you can progress and try to understand how they happen. You look back at it. So you cannot really. So a lot of books and many other places, people have tried to explain things in too many words and gotten into trouble. So the idea is not to try to do that, not to bring in things which you cannot explain, and just say that, just go along and understand. The minimum thing you want to visualize and picturize which works well is to think about these things as spin tops, spinning tops and things like that. And what you can imagine is that as the top spins, as its velocity decreases, it in fact actually goes around more and more, and then finally goes down to the flat. So those in-between states where it's actually reducing its speed, it goes through a place where it topples down. That's the superposition state. So this continuous tipping is something which actually goes on in the quantum system. And that's the physical reality which you perhaps will have difficulty in understanding. So in terms of looking at a simplest quantum gate, which is what we, in terms of computer scientists and electronics engineers would like to understand, it is like this. You consider an atom. This is the simplest picture that I could come up with, and perhaps there is that you consider a state which has an atom which has an electron, the simplest state, let's say a hydrogen atom. The electron is in its ground state or in its excited state. So you label them as 0 and 1. Okay, those are the two states. In terms of a classical system, it would be either one or the other. But in quantum mechanics, and that's the beauty of it, in this particular case, what happens is you can have this transition happen in such a way so that you can have a coherent superposition of both the states being present at the same time. And that is the thing which is different in terms of quantum versus classical. So in terms of classical, it is always this, the the right side is your answer. So if you look from that side, that's your left side. So the left side is always what you are looking at, either state 0 or state 1. But if you look at quantum, you can have laser light come in such a way that both of these two states are in certain level of coherence. And this is one of the ways of how you can understand this. Once you have understood this, you can look at it the next possible way of how people think in terms of implementations. So the first, or one of the easiest implementations, although there are many other, but this is not the first one, this is perhaps one of the first ones where implementation has been made, is the idea of using ion traps. So why ion traps and why not neutral? That's because ion traps are charged, and so they can be actually manipulated by using magnetic field and electric field. And so you can arrange a linear trap of this kind where these ions are kept in a specific distance away from each other inside an electrode state. So under this condition, you can have two conditions. One where you can address any one of these ions and have it in ground or excited state. That's one of your way of considering that. And the other one is to consider the case where you are going to have them at a certain distance away from each other or at a fixed distance. So this is at rest, or it is a collective motion of one kind. So you can have motional qubit states, or you could have internal qubit states, and in that sense you can have multiple of them operating at the same time, and that's how you build up your qubit structure or your computer so that you can use them and get them. Other popular technique which has been working very well in this area is something called a machine which is being used by spectroscopists for looking at molecules, or by medical persons for taking MRI imaging of your inside to get to know what is going on. The principle there is very simple. You have a magnetic field which is being applied, and your protons are aligned in one way or the other in the field. But you can also have other spins of nuclei which also interact, and so you can have a situation where, let's say, the carbon versus the proton are being aligned with respect to each other in a particular way. And this is one of the first qubits, which was again one of the first fields. So ion traps and this NMR were the two first qubits which were shown to work towards quantum computing, and a lot of the testbed experiments have been done here. One of the most difficult problems of this particular area, although this is one of the ones which became very, very popular for a while, and it was essentially my also entry into the quantum computing world, although I don't do NMR. The idea was that this is very simple. Your molecule is your qubit, so your entire computer is the molecule. So as long as you have a large enough molecule, many things happen. You can have our entire molecule act as a quantum computer for you. So this is the NMR quantum computing, which became very, very popular for a while. The difficulty in this case, however, is that to be able to know the signal to noise is very difficult, because as you can see that you are looking at one single event out of many possibilities, and this has to be done at a temperature where these systems are in their native state. In the sense that if this is a chloroform molecule, you want it to be liquid when you do the experiment, which means you cannot go very low temperature. You your signal to noise is not going to work in that cell. So you have to keep it at those temperatures. So under these temperatures, you have to make sure that you get enough signal. And so in practical sense, to get the enough signal to noise conditions from here, you have difficulty in scaling these things up to a larger number. This is where this particular approach, although one of the best ones perhaps in this field, died to some level. I mean, it's still used as one of the model systems to show how quantum computing is supposed to work and things like that. Every particular idea about quantum computing can actually be perhaps shown in this model, but it cannot become a practical quantum computer. So this is what I now actually tell you the bottlenecks. There are several attempted systems which are being tried, and many of them will keep on being tried, but they all have their difficulties. So the ion traps, cavity QED, quantum dots, NMR techniques, all of them have their drivers. For example, like I say, the NMR technique faces severe scalability problem, although it's the most successful because it actually has shown the maximum number of possible qubits as well as the maximum number of algorithms being tested out. It also, the other thing is that you need to develop schemes that will be qubit scalable. For example, extending NMR concepts to molecular spectroscopy, because in some sense, NMR is nothing but a spectroscopy. If you actually take that as a spectroscopy challenge into other kinds of areas, then it can happen. But then there are other issues. There are decoherence and control issues, and that's why. So one of the things which happens in quantum systems is that they are too small. In order to measure them, you really need to have a lot of them to be present to give you the measurable value, which is your statistical answer. So quantum mechanics is one solution, but in real world, to see it, you need statistical mechanics. So when you put them together, that's your real world. In the real world, you need enough number to get to your measurable count, and that's where you have this difficulty of mixing it up. In general, you would like to have optical schemes because you would like to actually have the information transferred at some point of time. And you know the best possible way of transferring information is through optics, because that's the fastest possible way of making any transfer. And so and also the secure. And that's why you would like to do that, but there are difficulties with just having the photon, which is again a quantum particle, to become your quantum computing material per se. That's what we will also get to here. So, generally, what are the requirements? The requirements are preparation of the initial qubit states. Then it's the manipulation of that so that you can result in evaluating 2 to the power n levels independently. So generally what's happening is that you are doing an exponential number of events being manipulated simultaneously, and that's the power of the quantum computer. But in order to do that, you need controllable unitary operation to be happening every time, which would be giving rise to the quantum logic gate. So one of the biggest difficulty in this field is that from the very beginning it's cross-disciplinary. A card-carrying computer scientist cannot come and write an algorithm which will work for a quantum computer. Similarly, a physicist cannot go there and say that this is my best quantum computer, quantum algorithm which you are supposed to use to a computer scientist, because most often the physicist doesn't know what it takes in terms of an algorithm for the computational principles. And so this dichotomy often creates a big problem. And and interestingly, the people who have made the mark in this area are often from neither of these fields. Charles Bennett, who is actually known as the father of quantum information, is essentially a chemist. He was an IBM fellow in terms of his chemistry and all that. For some reason, he was doing molecular dynamics of other kinds of things. And then at one point of time, he became interested in it, and then rest is history. BB84, which is considered to be the best possible information transmission approach, and the secure one is the Bennett Prasad 1984 code which they wrote, is essentially between him and the other guy, Prasad. So that's why it is often, I have a strong feeling also that in the initial days of the growth, it's often always the other people who are going to make the bigger impact, partly because they don't ask questions, or they're often willing to ask questions which card-carrying practitioners will not, or will consider them to be useless. And that's the problem. So if you are a computer scientist, you will never think that this is one way, this is the other way of doing it, because you are trained to be thinking in that sense. Whereas if you are somebody who others will never consider you to be a computer scientist, will ask or do things which you are generally not supposed to do, and you then create or do something new which others had always overlooked or not even considered. And that's perhaps the reason why in cross-disciplinary areas, fresh blood is often considered to be the best thing. So anyway, I'm sure people who are from the field also can learn and do a lot of very important impacts in this field. So the one of the biggest problem is the time scale over which these things have to be done. Part of the reason is that these particles being so small, to keep their information right there for a long enough period of time is also difficult, and that has given rise to the term which is known as ecoherence. Coherence aspect of all these information is very, very important, because that gives rise to a way of measurement and keeping them together for a very long time. But if they can be driven off, they get driven off from that point, then you don't have that information possible to be retrieved. And that's why the word ecoherence has become one of the major words of impact in this area. So a lot of work goes on in this area, and most of the time these time scales are in the region of 10 to the minus 12 seconds. That's where these events are going to happen. So in order, I think I have mentioned it a little bit before also, but here I would like to show you some of the important points which are that you definitely need qubits. I keep on saying, you might feel it's not very, it may be very trivial to think in terms of the beginning material, the qubits, you are hunting for it. It's actually an interesting question. It's like saying, in a computer, if you are asked what's a bit, 0 and 1 voltages, you never even think twice about saying that why are you looking for it. It's always there. But unfortunately, in a quantum computing system, even the definition or the usage of what is the best one as a qubit system is a big problem. You have to first be able to come back and say that I have a qubit system which I know is reproducible, is going to be reset all the time, is going to be available to operations and amenable to operations in the right possible manner, which gives rise to information processing. These are all the questions which are not very easy to be addressed all the time. And therefore, there are some definitions which have been made, which are like these are essentially two-level quantum systems. They are amenable to superpositions in such a way that they are isolated from the outside world. They don't want to be always interacting with the outside world, then you lose them. And finally, they are confined, characterizable, and scalable. These are the very important points there. You need to make sure that this whole process can start at a certain point of time. You cannot just say that I have it, and so I should be able to get somewhere. That's never going to happen. You have to actually be able to prepare so that you can say, I want to do these objective work with it. So there is a preparation phase associated with it. And obviously you need to do operations on it. So what are they? They are your logic gates. These are controllable interactions, and this has to be done from an outside world. You cannot imagine that within the system, bits are being manipulated and you are getting a result magically. That's not. That control has to be with the user, and that's why the logic gates are an interaction with the outside world. And then finally, these are, the second point is actually a superset problem, which is like you at least need single and two qubit gates, and in many cases you can kind of show that that could be sufficient, although this is not a necessary condition. So these are issues which are mathematical and with higher details. I don't want to get into those things, but there is a lot of inbuilt information which is also necessary when you do it. And finally, the readout. The readout phase is essentially going classical. So finally has gone classical in the fourth step. So final measurement which you bring back to the world is the classical. So we have been working in this area perhaps. So in India we are the second group to have gotten into this whole thing. The person who first initially, well, at about the same time as me, although he's very senior, had started on this area from NMR point of view, was Anil Kumar from IIT Bangalore. So he started on this area at about the same time that I came back to India and started working on this. 1998 he started publishing work, and I also came back at around that time. But my approach has been always different. I have been working towards the area of using light instead of using NMR principles. So we were initially supported by Information Technology Ministry as one of the exploratory projects where we started it off. And after a while, as it is important to know where you have reached, and if you are going to go to other places, you have to do other things with it. So I went away to do other things, but I'll actually tell you the way it has happened. We work with one order smaller in terms of time, so that this difficulty that is there in terms of 10 to the power minus 12 seconds is addressed better. So our laser systems are 10 to the power minus 15. So we are well in time, because we are 1,000 times shorter in time compared to the time scales that the other processes start happening. So we have at least 1,000 seconds advantage when we start working on these kinds of principles. So we start with femtosecond laser approaches. For the robust operations to happen, those are the techniques that we develop, and we work on the idea of interacting the light with the quantum objects, which are, say, molecules or other systems, which can give rise to the information processing that you would like to finally do. And finally, we are also interested in distributing the information, because we do recognize that at this point of time of the development, it's perhaps not possible to build the large matrix computer right away. It's possible to build smaller components which are perhaps possible to be distributed over a larger space, so that you can get this. So that's the reason why we have stuck to light part, so the information transfer can be done as fast as possible. So initially, this is our second phase that we have gotten into this area. We gave a break of about 10 years after the initial development, and then we went back to information technology, as they called us back, and were kind of curious, because right now there's a huge cohesive effort from the government itself in order to try to go back into this mode of doing quantum information and quantum computing area. And I was there on 30th March when finally DST signed a large overview grant system. It's called the AKTU-AICTE REACH program, where they will currently support around 4 or 5 teams with 51 projects. And I think the amount of money that has been allocated in the first phase is about 200 crores to start in this big area development. I am not a part of that part, because I am already supported and I am from the Information Technology Ministry angle, but we are the overseers of all these processes going on. So the idea there is to enable younger researchers who have. So I suffered a bit in terms of trying to bring in something to this country about 20 years ago. So I have felt that, when you are bringing in new technology, it's always good to have the younger people not feel the same kind of walking through regions where it's very difficult to walk through in the initial years. So I think these kind of enablings will help everybody a lot in terms of starting the new research in these areas. Our goal still remains the same, that we are mostly, because I work in IIT and others, is to have a lot of human resource development, good students and other researchers who can work in this field eventually. And our approach has been to initially start developing one of the areas of. So I have had earlier funds from other areas which were working on different principles, but we have now concentrated them to work towards the principle of trying to show a particular algorithm which will be useful. So there are various different algorithms. I might have mentioned them while we walk through, but let me tell you one of the algorithms which is quantum computing wise considered to be very robust, in the sense that if you demonstrate that, you kind of know that your qubit system is ready to show quantum behavior. It's a coin toss problem. It's known as the Joyce-Joshua algorithm. So basically, if you do a coin toss problem, you can either have a biased case or the right kind of case where you are not using a fake coin. And so this is basically finding out balanced versus constant function kind of a problem. So that's called the DJ logical problem. So we would like to address that to show that we are able to do that. There is another very interesting problem which, by the way, was developed by an Indian alumni of IIT Delhi who was doing his research in Cornell, didn't get his, sorry, he was a faculty at Cornell, didn't get tenure there, then he was taken up by Bell Labs, by another of our well-known scientists out there who's now back in India. He's a mathematician at that time. So anyway, so Grover's algorithm is something which actually looks for, it's a very important search algorithm. So if you have a situation that you have a single element that you want to find out of many, then Grover's algorithm, which is a quantum-based algorithm, says that you can find it in root n steps. So if you have n elements and you are actually going to do or find a single element out of that, let's say in this room, for instance, somebody wearing a brick shirt, there's only one. In terms of doing it by using classical method, you have to go at least n over 2 terms, because statistically you go around half the time you will get it one way or the other, and so it's n over 2 order. Whereas if you do it in the Grover's algorithm approach, which is a quantum case where all the information is been uploaded and superimposed in one state, it actually produces root n. It's not a logarithm, it's not an exponential enhancement in that sense, slightly less than that, but it is good enough to show that. So we had earlier shown Grover's algorithm, but there is a catch in Grover's algorithm. The Grover's algorithm, although it's a quantum system, it utilizes superposition principle and not another very important aspect of quantum computing, which is known as entanglement. So what is entanglement? Entanglement is something which is extremely useful, because that's the one which is used for quantum information transfer also. Entanglement is based on the principle that quantum mechanics is all about matrix manipulations. And in matrix manipulations, if you have noticed, if you multiply matrices, the size of the matrix grows. Right? It's not that your size of the matrix actually remains constant throughout. It's a determinant matrix with determinant multiplications where your size of the determinant will remain the same. But in matrices, the size of the matrix grows. And therefore, if you are given a final matrix, to be always able to tell which two matrices gave rise to that final large matrix is almost impossible. This expansion of space, which happens, is known as entanglement, because you cannot go back and tell exactly where it came from. And this entanglement is a very important thing, because once you get entanglement, your information security is extremely high. And that's why that's a very essential part of quantum computing and quantum information. So you can actually do many events without using that particular feature of entanglement, and one of them is Grover's. So in Grover's, you can actually do superposition after superposition and get the result, although you need more resources to get there, but you will finally get the result. Whereas in terms of certain other algorithms which are only quantum, you cannot do that. So the exponential enhancement you cannot ever get if you do that. So there are many issues associated with that. I can actually go through that in detail. In fact, I have a NPTEL lecture series. If you are interested, you can go back and see it. One of the things which I would like to mention is that Grover's algorithm, if you want to really employ it in terms of quantum way, then you apply it by using quantum Fourier transform. There, this whole idea that you can just get away by only doing superposition is not a restricted criteria, and so you can get the full benefit of exponential benefit. So the exponential space benefit that you get in quantum computing is all coming from the matrix manipulation part, which gives rise to entanglement. So although DJ algorithm is a much smaller algorithm, it actually in some ways preserves the very important criteria of entanglement. So we have actually thought that we will actually show the DJ algorithm rather than the other algorithms which has been implemented. The best of these algorithms is finally to show the Shor's algorithm. Shor's algorithm is the one which actually looks for factorization, and that's the one which is needed for for your RSA code breaking and other kinds of things. It also actually gives you a better enhancement in your encryption, because you cannot break something that easily. Now, a couple of quick things which I wanted to tell you when you look at lasers. The first thing is that so one of the things which we often talk about is the short pulses and other things. The first thing to notice is that electric field always at the end of the day is a wave, right? And when you truncate it, it's becoming shorter and shorter, which means that there will be a case where you will have oscillations which are placed within the envelope profile that you have chosen. So most of the time what happens is that you have a Gaussian which you have chosen, and within that there are a finite number of oscillations. Many a times these numbers are so large that it doesn't matter. In fact, most of the studies or things that you have learned, or if you go back to the physics books, always deal with situations where your oscillations within the field, within the pulse, is extremely large, and so you do not need to worry about the little inconsistencies of exactly where you started or where you ended, because the difference between that jitter in time is never going to tell if you had one more oscillating field or not. It's not possible. So that little difference is never to be seen when you do that. So most people, what they do is, and that's how almost all books are, they only talk about the envelope profile. You don't even worry about the underlying frequency. The underlying frequency is taken into consideration as the energy. All you talk about is that the underlying frequency is important, because is that an energy corresponding to the gap of states that you are looking for? If that's the way it is, then you can actually consider that to be an envelope profile problem with a right frequency. That's what you do. You don't even worry about the oscillating feature. If you go to time scales where they are really, really short, then that many oscillations will not be there. There can be very few. Those are known as few cycle pulses. Then this rotating wave approximation, which I just mentioned, does not work. And we have done work on this area also, but as of now, I'm not going to talk about this, because in most of the applications what we are talking about here, this is not necessary. So our lab essentially has half and half of both the fields, because unless you do both of them, which is both theory and experiment, you cannot go ahead with doing these kinds of experiments, with these kinds of research. So our most of the work has been dealing with theory and experiments. So how does the theory and experiment go with? So these are things which are there from very long times. What you are after is that for an ideal two-level system, if you read, what you would expect is that the population, if you do the simple calculations, let me actually do the calculation part before I come to this slide. So you are essentially dealing with a two-level system where you are asked the question as to how you go to the next state when you apply this. You can make the problem much more interesting, maybe complicated, maybe by saying that I don't have the exact match, and with the idea that lasers have a lot of photons and they can be of the same kind, you can also get to a situation where all the vector additions take you there. All these are possible, and there are terms for each of them. This is a single photon transition, that's known as multi-photon transition, and you can develop models for all of them. But at the end of the day, story is you have two states, and for computing purposes, you are going to see how that approach goes ahead. So if you apply these models, then you will find that you are either going between the up state to the ground state, down state, and somewhere in the middle you will be always getting. And as a result of that, you would be oscillating that. And this was shown long time back by none other than Rabi, and in fact Rabi Rabi oscillations is the one for which he got the Nobel Prize, which says that the light matter interaction essentially should go back and forth between ground and excite state. But although that is said, very well said, experimentally it took a very, very long period of time. So this was almost, it was long before the time of lasers being invented. These were in the 40s when they were actually shown, and I think Rabi Nobel Prize is in the 40s. And the lasers were invented in the 60s. But it was in the 90s or late 80s that it was shown that oscillating Rabi oscillation can actually be seen in even a perfectly level system. Why is that? It's because although in ideal sense you have a single atom, you have a light coming through, it never works like that. Even if you consider a single atom condition, first of all, that's very difficult to do. And if you can get there, and one of the ways which again fetched another Nobel Prize, which is molecular beams, which is basically go to a so it's almost like you have the aeroplane level technology going on there. You evacuate, you go to very small Mach numbers so that you only get a few molecules going through a jet expansion, and then you essentially keep a certain section where only laminar flow is happening with a few of these molecules going through. Then you have a laser go across it, and then you are perhaps simulating a situation where you have one single molecule interacting with the light. And that was one of the cases where these were attempted. In fact, the easier approach of that is also to take a solid state system like an anthrazine molecule crystal and then dope it with a phenanthrene. They sort of apparently look the same. I'm a very bad chemist, although I'm supposed to be a chemist. Been physicist all through my life. So the molecule, one of them look like the one which is being hit by the laser, and so you can actually consider that to be a one atom or a one molecule effect if it is two states. See, in terms of the physics principle, it doesn't matter whether you have a molecule or an atom as long as you only have two states. The difference between an atom and a molecule for a physicist is only when many springs, which are the individual states, get coupled. Otherwise, to them, it's always one spring, one frequency. That's what it matters. So that's so in simplistic terms, initially when the laser was invented, physicists were of the impression that they are going to put the chemists out of business because they will now have the single frequencies of every different molecular states, and they will make the drugs just like that. You give the precursor, the answer is right there, because you just need one frequency which they have from the laser. It comes, cuts with a scissor, and you get the right molecule. It never worked. Partly, the first thing which people learned of that is that you are never having single oscillators, single frequency oscillators. They are always coupled to each other. So that's the area of coherent control, which I basically worked for many years. So anyway, what happens here is that after a lot of work, what you end up seeing is, you on an average, since you are not able to see the oscillations, you will see a 50-50. And that's exactly what happens. You have a 50% population in the ground, 50% population like excited state, even though you are using coherent light with a laser. That's because of the averaging that happens whenever you make a measure. You have 50% of time population in the excited state, 50% in the ground state, and that's what you see. And that's the line that you see, which is a typical experimental system. Now, the first thing which people wanted to, at that time, people wanted to know, that's also because this is the time which I did, this is the time of work which I did with, it was Ronald Reagan administration, which we were looking for, this was in US, they were looking for chemical lasers. So iodine used to be one of the molecules where they thought that you can make a laser out of it. So they wanted all the population to be in the excited state, so that you can, the iodine can, the excited state can go down and you have a chemical laser coming. But the difficulty was to get all the molecules in the excited state. It's very difficult. It doesn't work. All the time you get a 50-50 population. So the idea which was used at that time, which we did, was to actually use the idea of what is done in NMR, which is known as the adiabatic passage, which basically means that you are doing this in such a way that the frequency is changing while the system is moving, so that the population goes into the excited state before the system comes to know that it has been there. And by the time it learns it, it doesn't know how to come back because the frequency is gone. It is a chirp frequency. So that's the way you could get to the excised state. It was possible to be done that way, at that work which I did was at that time partly done with Nano, who got the Nobel Prize last year for her chirp pulse application, which she had done before she came and worked with us. So that was during my PhD. So anyway, the idea behind this work is to show that you can actually go ahead with that. But all of this was based on the idea, which is always used, is that molecules and whatever we are looking at are devoid of this motion. We never, in classrooms and whenever you have been taught about any spectroscopy or harmonic motion and all that, you have never been told that the molecules are actually physically moving. That's never taken care of. You always say that this is stationary, and that's why you can represent it that way, and it's only the internal coordinates which matter. Doesn't matter with the other coordinates. So in this field of coordinates, you can go ahead and do all this math. I'm going to skip them because that's not important. But it's almost always important to show this, that you are actually looking at the intensity of interaction with the laser, and you can in fact show this kind of a oscillation, which is the Rabi oscillation, theoretically at least. And if you want to do real going up to the population to the other case, then you have to use a frequency change. Interesting part to note, however, which is very important, is to note that when you talk about shorter and shorter pulse lasers, you are essentially going away from what you have learned about lasers. Lasers is supposed to be single frequency, right? But that's no more true when you go to short pulse laser. You have 47 nanometers bandwidth sitting in there, so that many frequencies present there when you have a shorter pulse, like a 24 pulse. Today, with an attosecond pulse, you can imagine that all the frequencies that you can ever think of are all present. So then why is it a laser? There is no meaning of a laser in that sense. It is still a laser because there is a coherence of all the states, of all the wavelengths associated with them. That's the difference between a scattered light and a coherent light. So these lights don't hurt you because their photons are coming in all scattered manner. There is no correlation between one photon to the other. But had this been a laser, whoever sat under it would have destroyed their eyes, partly because of the way all these things work. So that's the difference. But the frequency component is terrible if you look at it as one signal versus the many of them. So generally you have to now think what happens in the molecular state though, that whenever you go have a ground state going to the excised state, the excised state has the entire population spread out instead of being somewhere in one multiplier. So one of the control problems was to see if instead of populating so many states up there, if you can do one of them. And this was one of the ideas which we used. This is again, if you think about it, this part of the work in fact was done with a guy who was working in the electrical engineering, and that's why you can understand why this is looked at this way. This is a reverse engineering problem. You have a problem where you want to go there, you reverse the problem and you get there. So it's a reverse engineering modeling principle which is used, that you, instead of spreading it out, you start with such a pulse which actually will become a nano. So you will chirp it in such a way so that it actually goes to to a narrow pulse in the end. And that is exactly what was done here. So these were the guy who used it later on. Ken Wilson is no more, but anyway. So many of these essentially are built on using large matrices, simulating these kinds of systems. And for a physicist, basically a larger and larger molecule would just mean a larger and larger matrix. So we are anyway doing, and when you solve them in the Schrodinger equation or the Heisenberg problem, it's essentially a set of linear equations. We are actually solving in the matrix method H psi equal to E psi. These are basically a system of linear equations which are being simultaneously solved. And that's exactly what you are after when you are doing this. So in this method, what you are after is trying to see if you can take a situation where many states will individually behave as if they are identically coupled or set to one state. So here is an example of a problem. If you have many states present instead of two states, they start moving the population away between them, and that's decoherence. since toxins. And you don't want that. That's exactly what you want to stop. So in terms of model, you can actually show that you can prove that to happen. So initially, when we did this work, it was possible, it was done with a non-physical shape of a pulse, which actually went up and down. That's very difficult to do. But later on, we found out that we can actually use other ways of also doing this. One of the frequency, which is a much slower moving frequency over the region, was able to do this kind of work. So we have developed this model, and this is known as model of intermolecular vibration and relaxation. Now this part is somehow related to chemistry, so I can justify my status in chemistry. But the advantage is that you can actually take it to a bright, equal superposition of bright states. So that many states now become accessible to your qubit. So this is like setting up of qubits. So all these equalized states are the states which you can now use as qubits. So now the next stage is, if you have generated them, is to apply a control knob so you can do a logic operation. So this is how you define a qubit. So I went through all these roundabouts to try to impress upon you how to create it. That's the whole job, right? So that in itself takes years. Once you decide on what you have gone to, then you want to use them to make and do a control knob, right? One of the simplest one in this area is frequency chirping. That's the one which actually works. And now that since Donna got the Nobel Prize, I get to show her. Second Nobel laureate, right, in physics. She's responsible for this amplification technique, and so I was a PhD student when she came as a postdoc with my guide in Princeton, and this is where we basically used this part of our work to do many of the development that we have been talking about. And then when I came back to India, I actually did it myself to set these things up and then put it through a system which is known as a molecular beam chamber. Once again, this is a beam chamber or something which Dudley Hirschbach and others had done. Polanyi, Hirschbach and Yantili got the Nobel Prize for building this years ago. So we use that system. So this is actually something which we built because it's much more expensive to buy it, so we ended up building it. It's not that difficult. You have to give the designs to the machine shop, or nowadays there are private machinists who will do it for you. And the time of flight we bought, and the rest of it is something which you can put together. It's 10 to the power minus 10 torr, very low. And you inject the gas in there, let it go to a laminar flow, and then select it out with a skimmer, as they call it. And from there on, you do the beam chamber analysis. So you can actually look at a single molecule study in this sense, a true single molecule study. So many of you, if you have now followed some literature, there is also single molecule studies, but those are known as statistical single molecule. This is a true single molecule. There is a difference. So in today's world, there is a lot of single molecule research going on, and that is done in liquids, but that's a statistical single molecule. And you make a lot of studies, you reduce the concentration to a level that on an average you are seeing one at a given time. So statistically you can see a few, and that's a statistical one, but that's not a true single molecule. This is a true single molecule. You can count. And using this principle, you can in fact show that you have control over chemical dynamics. So this whole story that I told you years ago, which was going on, saying that you can actually break a specific bond precisely because of the laser, took so many years. So in fact, I think this is one of the second or third work in this field, which specifically shows that it is possible to break chemical bonds as per will. So what we did was we basically, it's a same molecule. So we also went through a little bit of a trick because it's not that easy to do it. So this cyclopentadiene, two of them, when they come together, it's a dicyclopentadiene. So if you look at the mass spec of this, then you have only two peaks, one coming from cyclopentadiene and one coming from dicyclopentadiene. So now if you can actually break the bond which makes the dicyclopentadiene, then you will be getting your cyclopentadiene side, right? So we took this dicyclopentadiene through that jet, had one of them present when we were hitting with the laser, and with a very specific kind of a laser property. And then we were able to show that we can generate the cyclopentadiene, which as per the frequency which was helping us, so relative ion is increasing, showing that we can actually control this by using the chirp of the laser. So that was the basic idea of this entire story. So that was possible here. But this is sort of like taking a walk on the other side. So if you really want to do a model or a knob which is on demand, then you can't just wait to see only infrequent events happening. What you would really need is an arbitrary pulse. Now it's like saying that I want my logic gates in a computer having different voltages. In milliseconds time scales, it's easy. You can always think about it. But you should remember the time scales that I am talking about. Our laser is 10 to the minus 15. So in those time scales, there is nothing available which actually can modulate. That's the problem. So what do? You do something which optics allows you to do. Optics actually is very nice. It allows you to do Fourier transform physically. You go to the Fourier domain. Once you are in Fourier domain, the time doesn't matter. So you pluck out your frequencies as you want in the frequency domain, and then produce the shape that you are interested in. That's essentially our USP in terms of pulse shaping, which is basically taking the pulse into the Fourier domain and then modulating it in the Fourier domain by using a modulator. Various different modulators have been used. This is a programmable one which can be done, and that's what it is. So with this, you can do Fourier shaping, and this is the electrical engineering kind of a diagram to show you how it works. You can do this by using arbitrary waveform generators in the Fourier domain, and you can do it with the conventional electronics. The only thing which you have to do is you have to actually pluck the right pulse at the right time. So you need a Pockels cell. So the Pockels cell is the one which actually runs at proper frequency to get it. Up to this, the industry standard has been 250 kilohertz. Right? So at 250 kilohertz, you can do this. So at a 250 kilohertz speed level, you can do this job and everything is fine. So the gas phase way of doing things, which I just explained to you, works. And that's why I could do those experiments. Now we want to scale it up. So when did I go back to information technology that we have done something? This was something up to this I had done about 10 years ago. And everything which I demonstrated here was within the last 6-7 years. But I waited. And the reason for my wait was different. The reason for my wait was that this speed is way too slow for doing anything which will take me from the gas phase, beam chamber, because that's not scalable. Okay? Imagine you being asked to carry this large of a machine all the time. In fact, that's the smallest scale you can ever think of. A car-sized computer with you if you want to do anything. That's the best scalable thing that you can think of, miniaturization of the system that I talked about. You would not like it. Nobody will like it. So in order to go further, I needed to develop something where this background had to be stopped. And one of the places where this had to now be taken care of is that I cannot ignore this theoretical principle that you can just look at internal states and go away with it. You have to go back to this fundamental problem that the molecules are always making. How do we keep the molecule at one place and do the work without using a gas kind of a principle that we have done? Interestingly, it also got the Nobel Prize last year. 2008, the second Nobel Prize was on optical devices, which essentially works on the principle that, by the way, it was not by design. It so happened that these two Nobel Prizes came last year. We have been working on it independently in a different way for our different goals, and they were finally recognized last year, although they were, at least the tweezer part was missed several years ago. the one place where living long is going to be good for you. So if you are a scientist and you want to have a good life, please have a good life which lets you live long, because the accolades sometimes come very late. And for instance, Nobel Prize is never given posthumously. So Ashkin would not have gotten his prize if he had not lived for 94 years. In fact, next couple of months later, I'm going to meet him again. I met him earlier, but this time, after his prize, I'm going to meet him again in a place where, fortunately, I'm also being awarded the fellow with him in the SPI. So we'll see him there. So the idea there is that you have a photon flux, which means a lot of photons coming, right? And those photons are there, they have a flux which imparts momentum to the particle, and it's able to freeze its motion. That's the basic idea. And for that, you need a specific kind of the photon flux to be shaped, which is a Gaussian. And if it is a Gaussian, then because if it is not a Gaussian like a rectangle here, it will actually not be able to trap the particle. It will actually run it away. So you need a paraxial Gaussian mode beam which will do this job. So this was something which he had noticed years ago, and it is based on the force balancing issue which leads to stable optical tap, and it's the balancing act of the gradient force which gets the scattering to be balanced, and that's the way how he was able to do it. And this is the trapping potential which works. It follows, it's in the simplest form, it's like a harmonic oscillator, Hooke's law, and the force equations can be pictorially shown like that. Every time you can make the particle come to the focal spot, and this is how it gets. So ultimately, the momentum transfer of the photon, which puts the particle in place, and so last year he finally was recognized for it. So, but this particular model would not work for us also still, because we are still in pulsed world. So the first thing we had to test, which we started testing out about that 10 years ago, was to see that a pulse laser actually indeed can trap. And what we found out is it in fact can do that. In fact, it's better. It has another advantage. What is it? It actually imparts nonlinear effect. And because of its nonlinear effect, at the focal point where the particle is going to be trapped, it by itself will tell you that I am here. If you can take a particle which has a nonlinear property, then when it comes to that point, it will by itself announce that it's there, and you have a trapped particle. Because nonlinearity is proportional to intensity, and that is possible only with a pulse. So we used this technique, and by itself, immediately we saw the benefits of it. We could trap very small particles, because particles which were otherwise not possible to be seen are now able to be seen because of nonlinear effects. And so with two photon imaging kind of ideas, we could immediately see smaller and smaller particles. So initially we took this technique to show that we can go down to very small particles. So at that time, this was the time we got distracted a little bit, I have to tell you. Partly because that was the year when super resolution microscopy got the prize. And so we immediately recognized that we are into the super resolution regime, because these particles are way below the wavelength of light. So we were at, initially we saw 100 nanometers, we were using 800 nanometer light. Then we went down to about 14 nanometers using 800 nanometer light. So which is, by far extremely high super resolution microscopy in that sense. So we had already demonstrated all this. So this was part of connected to what we were doing for Wellcome Trust. So Wellcome Trust had asked us to develop a better microscopy standard, and that's what we were doing, and that's when we got into this. So I was not doing quantum computing at that time. So I actually had walked away to other areas or French areas to develop so that we can come back. So these are the things which we were developing. It turned out that we can do high repetition rate pulse lasers to also do these. It also yielded something in other interesting things. We also saw that you could univocally assign structures when you are trapping. And this is actually very interesting because this has a very high chemical engineering application. You can actually have multi-particle optical trapping, which allows us to visualize colloidal aggregation. Not only that, colloidal aggregation geometry was also were also something which we were able to show while using this. Now, all of these developments also helped us to find out another advantage of using these trapping, but we had to do an important step here. We had to actually show that the traps that we generate are calibratable. See, the bigger problem of traps is that they are not calibrated. So, these traps which are generally used for biology are essentially used to just hold, move. They are not interested in on a day-to-day basis how that hold, move part has to do in terms of some measurement values. But what we were trying to say was much more than that. In fact, what we developed something here is something called a viscometer and a thermometer, nano thermometer as a result of that. And so we had to calibrate this. So what we did was, in addition to regular trapping, we also gave a steady motion to the microscope slide, so that came as an additional frequency signal that we could use on a daily basis as our trap model, as a calibration device. And we were able to actually develop something called a thermometer and a viscometer at a nanoscale. So these were the other developments we did. Now that we know that we can do all that, we combine this with the pulse shaping, and our proposed methodology is that we can do this trapping as well as the pulse laser based studies to do that. But there is one more catch still. That catch is, I can only do it at 250 kilohertz, the trapping, the pulse shaping. I cannot break that barrier so that I can shape at that speed, which is going to do the optical work for me. So we had to revisit pulse shaping again. And what we found was that this was the way how we were doing things. We were having the light come through, we were interacting with the radio frequency, and it was going out, and we were looking at the cross correlation to characterize it. Depending on the shape that we put in, we were generating a new pulse every time. Fine, that's okay. If you go to the oscillator, so that was how you do an amplified laser. If you use an oscillator, this is the level of signal that you do. In order to look at it, you have to actually do a lock-in measurement. But those are all fine. Those are just additional details. There was also this story that you could go along with the path, but that doesn't do anything but compression. So we revisited it, and we saw that we were doing something called low repetition rate pulse shaping, which is like triggering problem. If you do it trigger right, then you get the right pulse. If you trigger it wrong, you get the wrong pulse. And all we had to do was to trigger it right, so that we got the right pulse with the right delay to do the triggering. Okay? Now, when you go at high repetition rate, there is actually a surprise. There is no synchronization anywhere possible, and it's not needed. What does it do? It does this. The interaction just generates all of them in one shot. And so only these are the ones which are right, the rest of them are all messed up. But if you count now, it's actually important. What you find is that out of 9, you have 3 which is right, and the rest are not useful. Right? So if you now do a comparison between these two methods, in one case you are only taking case 2, which is what you get, and that's where you get 250 kilohertz. In the other case, you can actually get 3 out of 9, which is the correct one, but you don't yet know how to talk about it. So we said, okay, anyway, whatever it is, we are looking through cross correlation, we are looking at the signal, why not look at it? But before doing that, we wanted to do one more thing, which is to use this principle which we had done earlier also. In the Fourier domain, you can actually add a phase, and what it does is it actually gives a delay, and this is a rapid tuning delay which is done for communication purposes. You can delay your pulses with respect to the original one by this so when we did the pulse shaping in the same technique this time, what we find is that certainly we cannot get the shape that we wanted because not all are getting shape. 3 out of 9 are getting shape. So you have the structure breaking through. But I also showed you one other thing, that's why I showed it to you, that we were able to delay the pulses one way or the other with respect to the. So we coupled the two and this gets separated out. Okay, we can either delay it further or backward depending on the sign of the phase. And if you want it to be a perfect rectangle, you can now do a feedback and you can actually get a very good shape. This is exactly how you can generate it. And we chose to show you this one because, see, now what has happened is that, so finally we have generated this shape, which is whatever we wanted. Now this is running at a certain frequency, that's all right. But more importantly, even this is now running at 10 megahertz. That is 40 times more than the current industry standard. And what happens when you do something like this as a paradigm shift? If it is you are competing with industry, your paper doesn't get through that easy. So it took me a while to get it through, but I know many people now, so it doesn't work that way. The guys from the industry, whoever was the referee, so there were 3 referees. One of them happened to be from industry. He was trying to delay it. Called up the editor and they said, what's going on? We'll find out. And then they immediately removed that and gave it to somebody else and published. So that's a different thing. But generally speaking, yes, if you are actually pushing the limits of the industry, then people are from industry, they don't like the idea that you have now rebuilt your entire industrial principles to get it going. So this is what we have just achieved. Now the advantage of this is now, if you notice, in fact we didn't have to wait so long, we didn't get it at that time. We could have always left this and delayed it. Even if it was working at 250 kilohertz, it was good enough for us at that time itself to go back and try in the liquids, which we didn't do. But now that we have anyway gotten to that point, we can do a 10 megahertz running of the logic gates while we have trapped the particle and then do the job there. That's the idea, and that's our current development. So this is our technology development that we've done over the years to get to this point. And what we are expecting is that our aim would be to sort of try to develop a system which will be distributed in terms of computing. I don't know how easy it will be. It will also require a lot of theoretical input to be able to decipher how to break them down in the quantum sense to get there. As I mentioned earlier, it's not that easy. And we do have one more control which we didn't exercise here. The traps can actually be controlled by using polarization of light also. So that's another control bit that we have. We haven't tried that yet. But that's going forward problem. And with that, I've been talking to you for over an hour now, so I'd like to stop and take any questions that you have. I'd be happy to answer.
So when we are having multiple input states and with the problem of decoherence, then how we will able to study 135 alpha for bright states for coupling and 226 alpha for decoupling? Then how we will.
Oh, no. So what I have done as of now for this particular case, where we are just looking at, this is just looking through how the shape that we have generated. This is an independent measure of a correlation of the original pulse with respect to the pulse that are being generated. Okay, so here there is no other measurement. It's like a so this is basically a camera kind of a thing, which is measuring the correlation between the original pulse and the pulse that you are generating. So there are no issues here. We are at this point of time trying to know how many of the pulse that we are generating, which is the real shape. Right? Now, what I am arguing is that if you are trying to do a single element which you are trying to address by the light to do your knob control basis, you want to keep it at a given place. So you need the photon flux. So the photon flux can either be the same light, which is running at 10 megahertz now as we have done, or since, see, these delays that we are talking about only matter if you want to do certain things, but if you want to use in terms of flux of light and keep it there, this light which is always present at say 60 megahertz or something, there. At around 10 megahertz, you will be having your modulating frequency coming, which is here, right? So every 10 megahertz, you can try to do something with the object which you have now placed, because with photon flux, which is immobile. So you can address that. The difficulty which was happening is earlier that you did not know who you were addressing, because they were moving like anything. Every time you created a logic operation, you never knew in a liquid or in a place where you have not isolated one by one. You never knew who you were addressing. You had sent your information or you had sent your logic, but it was like hitting in the dark. Who is being addressed to was not known. Now, because of this combination, you know who you were addressing, and you can get to have some feedback as a result of that. That's that.
From that feedback, we will decide that there is a coherence of this.
Yeah, so those are later on to develop as to see how they go ahead with that. Those things are not clear yet. So the first experiment on that application is yet to be done. So it was, so even my project was given on 1st March or something for this new development. And you are doing it in the quantum sensor. Whenever you have a quantum register and you apply Fourier transform to it, then it's a quantum Fourier transform. So any of these atomic molecular states, whichever you are going to get into that state, if that works out to be in a condition where you can apply, then it will work. So that's critical for doing something called Schur's algorithm, where you are actually looking for.
We are generally using this Fourier transform
So, right. So, imagine Fourier transform being done only on quantum objects. Then it's a quantum Fourier transform.
Science, so how come it will be commercial and how it will be benefited apart from the industry?
So, I mean, initially, these kinds of apprehensions are not at all an issue. That is okay. But if there are benefits out of it, then commercialization will always happen. So, nobody knew that ENIAC will today come to a ThinkPad, for instance. It was never thought of. In fact, I'll tell you something. There are miniaturizations which have taken things to a point which you cannot even imagine. So when the mobile was first talked about, mobile phones, how many of you remember Jurassic Park? The first one, right? Even in Jurassic Park first part, you will see that they were talking about cellular communication, and that was the futuristic, extremely futuristic thing at that time. But even that was huge and large device, and it actually required some place to station it and to be. And there was a joke by this, and also the night vision goggles, for instance. There was a joke by that by the guy who was eaten up first by the directs. The finance guy. It's always like that, the scientists always make fun of the financial guys, but we have to take their money, otherwise we cannot survive. But anyway, that fellow, the first thing he told the kid was that, is that heavy? And he said, yes. Then it must be expensive, keep it away. So it's like, we associate certain things to some things. And that's always there. It's not a problem. Point is, when it comes, when the need comes, if the demonstrations are there, I'm sure it will go ahead. And we have a lot of faith on our engineers. That's what I would say.
Thank you.
Thank you, sir. Thank you for such a nice talk. We have learned so much in the physics. So, on the behalf of the Center for Advanced Studies, I would like to give a token of honor.
Thank you.
Thank you.
Cut, cut.